All right, hello everybody. Today we are going to start into a totally new concept. Today we're going to be talking about moles. And we're not talking about the moles on your cheek, and we're not talking about the moles, those little fuzzy critters that show up in your backyard and dig tunnels and make your family get mad at all the tunnels in your yard. We're talking about a unit of measurement. But before we jump into moles, I would like to make sure that you have several things on your desk. Make sure that you have notes, a place where you can be taking notes. Maybe some scratch paper would be great and a pencil, but also a calculator and your periodic table. So pause this if you need to, but make sure that you have all those items handy. As I'm going through some of these calculations, feel free to pause the video so that you can catch up to the calculations. I tend to talk a little bit fast, and then continue on as needed. All right, so what exactly is a mole? A mole is a unit of measurement. It's like a counting number, like a dozen. So we can say we have a dozen eggs, or we have a dozen chairs, or we have a dozen computers. We can also say we have a mole of something. But a mole isn't 12 of something. It's an enormous number, and it's based on a scientist whose name was Avogadro. It's based on his calculations. So Avogadro's number is what a mole is. And Avogadro's number is 6.022. I usually just say 6.02 times 10 to the 23rd. That is absolutely a number that you need to know. If you don't accidentally memorize it, then you need to write it on your periodic table to make sure that you remember that Avogadro's number is 6.02 times 10 to the 23rd. And that tells us how many items there are in a mole. So 12 is how many items there are in a dozen. Avogadro's number is how many items there are in a mole. Usually, when we say items, we're going to be talking about atoms and molecules. There's not very many other things in the universe that we would want to talk about a mole of because it's such an incredibly large number. Now, I have a few little pieces of unimportant trivia, but it just gives you sort of a sense of how big that number is. 6.02 times 10 to the 23rd. We can't even really conceptualize that. So if we had a mole of hockey pucks, that would equal the mass of the moon. If we had a mole of basketballs, it would fill a bag the size of the earth. If we had a mole of pennies, it would cover the earth a quarter mile deep. That's a lot. So it's a super, super big number. All right, so now we understand that a mole means 6.02 times 10 to the 23rd of something. What is molar mass? Well, molar mass is the mass of one mole of whatever you have. So in this case, we're going to be talking about elements and compounds, or atoms and compounds. So will you take a look at your periodic table right now? Look at the periodic table and look at the numbers that have the decimals on them. So remember that that's the atomic mass. And remember, the atomic mass is the average mass of one atom. So like for carbon, 12.011 is the atomic mass for carbon. And we call that average mass atomic mass unit, AMUs. 12.011, that number also tells us, wait for it, the number of grams in 1 mole of the substance. That's what molar mass is. So let's try that again. Look at carbon. If you have one carbon atom, just one, well, okay, so an average carbon atom, the average mass is 12.011 AMUs, atomic mass units. So that includes your protons plus your neutrons, basically, and we're ignoring, for the most part, the electrons. However, that 12.011 also equals the number of grams if you had 1 mole of carbon atoms. So what is 1 mole of carbon atoms? It's if you had 6.02 times 10 to the 23rd carbon atoms, it would have a mass of 12 grams. So you can kind of imagine what 12 grams is. Our balances in the laboratory can definitely measure 12 grams. So, you'd have an amount of carbon that's about yay big, and that would be your 12 grams. That's 1 mole of carbon. And we typically round it to 2 decimal places, although you'll see me being a little inconsistent in some of my answer keys, and that's because I use significant figures, and we haven't necessarily taught you significant figures. So go with 2 decimals, and if you stick with 2 decimals, you're safe. So I want you continuing to look at your periodic table. I just did what the molar mass of carbon is. So 12.01 grams in 1 mole. So we write it as grams over moles. So it's grams per 1 mole. But if you need to break that down, grams per 1 mole, that's what that means. Look up aluminum. Its molar mass is 26.98 grams per mole, and zinc is 65.39 grams per mole. Why is that? That's because each of these atoms, each of these elements is a little bit larger and has more protons and more neutrons, so they have a greater mass. So when you have a mole of them, when you have 6.02 times 10 to the 23rd, their mass is greater and greater depending on what element you have. All right, now let's look at the molar mass of some molecules. So water is H2O. So you need to have 2 H's and 1 oxygen. So how do you calculate that? 2 times the mass of 1 hydrogen, 1.01, plus the mass of 1 oxygen, 16.00. So the total molar mass, if you have 6.02 times 10 to the 23rd, water molecules, if you have a mole of water molecules, it will have a mass of 18 grams. We could put that on the scale and it would say 18 grams. Vice versa, if I have a mass of 18 grams and I measure it out, 18.02, and I measure it out, I can say, hey, everybody, there are 6.02 times 10 to the 23rd water molecules here. Now, that's a little bit of an exaggeration because my balance isn't precise enough to say that exactly, but that would be an estimation that I have a mole of water molecules. All right, let's try sodium chloride, NaCl. So look up Na, look up Cl, add them together, and the mass of 6.02 times 10 to the 23rd NaCl ions together would give you 58.44 grams in 1 mole of salt ions. All right, and then same thing with all these. These are just additional examples. Sodium bicarbonate, add the sodium. So take a look and make sure you see how it's broken down. Sodium is 22.99. 1 hydrogen is 1.01. 1 carbon is 12.01. And then 3 oxygens would do 3 times 16, which is the mass, the average mass of 1 oxygen atom. Okay, and then sucrose, it's going to get bigger and bigger and bigger. Sucrose is a larger molecule than anything we've seen in these previous examples. So its mass is 342.34 grams in 1 mole. What are we telling us? Or what are we saying here? If I measure out, it's going to be bigger this time, 342 grams of sucrose, I have 6.02 times 10 to the 23rd molecules of sucrose in that sample. All right, so now we're going to do some math conversions, and this is where your calculator, your pencil, your scratch paper are all going to come in handy. You should also have, and if you don't have that already, if somebody hasn't handed it out, get that. You need your mole roadmap. We're going to walk you through the mole roadmap. I'll show it to you I'll show it to you in just a second. But the mole roadmap is a cheat. It's a crutch. It's something that I'd like you to use maybe today, maybe tonight, and then I want you to be able to set it aside and not need it anymore. So I'm going to show you how to do these conversions, and I'm going to show you what it looks like to use the mole roadmap. But then I want you to be able to go, okay, I can figure this out without using the mole roadmap. Okay, so let's try some problems, and let me just give you a rough idea of what we're going to do. Let's say I tell you you have 3 moles of salt, and I want to know how many grams that is. So we're going to have to go to the left on this. Is that the right direction for you guys? It's to the left for me. I don't know if it's to the left for you when you have it reversed, whatever. We're going to have to go this direction, and we're going to have to convert from moles into grams. Vice versa, I could say I have 52 grams of salt. How many moles is that? I'm going to need to convert from this direction to this direction. In order to do that, I need to know the mass of 1 mole. So I said it was salt, NaCl, so I'd have to add an Na and a Cl, and that would give me the molar mass, and then I can do those conversions back and forth. Let's say instead I want to go from moles to numbers of particles. And when we say numbers of particles, we're talking about atoms, elements, molecules, number of particles. And that's Avogadro's number. That's 6.02 times 10 to the 23rd. Whoops, there we go. And that's how many of the items there are in 1 mole. So let's say I say we have 10 moles of something, and I want to know how many particles, or I want to know how many molecules, or I want to know how many atoms that is. Then we would do the number of moles times the 6.02 times 10 to the 23rd to calculate that. So, and then we can go backwards too. Let's say I'll give you some crazy number. Let's say we have 4.68 times 10 to the 26th molecules or atoms of carbon. How many moles of carbon do I have? Well, we're going to use that 6.02 times 10 to the 23rd to calculate moles. Okay, now I've introduced that to you. Now I want to show you the mole roadmap, and you should have the mole roadmap in front of you. It's the same idea, but it's showing you a little bit more directly how this works. So let's go ahead. Actually, I'm going to back up. Before we do that, let me give you an example of how we convert things. I'm going to switch screens. Give me just a second to make this work. I hope it'll work. I'll be disappointed if it doesn't. I gave you a little sample problem. I thought I gave you a little sample problem. I did give you a little sample problem. Here we go. All right, so it says we're going to use something that's a little bit more understandable, something kind of numbers that you can imagine a little bit better than these Avogadro's number. So it says how many eggs are in one train boxcar? So let's pretend that we have a boxcar that is completely full of eggs. How many eggs are there in this boxcar? I will tell you that I made up these numbers. I'm sure they're completely miles off from reality. I was just trying to show you how we do this kind of a problem. Okay, so let's take a look at what they're asking for. They're asking for how many eggs. So that's going to be at the end of our equation. I'm going to get this written here. What we don't know is eggs. That's what we're trying to figure out. That's supposed to be a question mark, everybody. I didn't make a very, should I write a little bit neater than that? Let's try that again. Okay, so the question is how many eggs, is that a little bit better, do we have? So we're going to start with one boxcar, and I'm going to write that over here. So I'm going to write one boxcar. Now, there are several different ways of showing these conversion factors. I'm going to call these conversion factors. I'm going to draw a line like this, and I happen to know that we're going to need to use all three of these conversions. So I'm going to go like this. And I'm going to have a conversion factor here and here and here. And I'm going to make those go away because I don't actually want them there. Okay, so if I have one boxcar that's over here, how many eggs am I going to end up with over here? Well, with the information that I have here, I don't have enough information to go directly from boxcars to eggs, but I can go gradually from one conversion to the next to get myself 2 eggs. Give me a second. I'm going to erase my question mark now so that we have space for it. Okay, so let's go ahead and jump in. Let's start with the first thing. We have one boxcar. The information we have here is that for 3,000 crates, there are 10 boxcars. When I do a conversion factor, super important. If you can remember this, it will make you super happy. You want to put the unit that you're trying to get rid of on the bottom of the conversion factor. So here's my conversion factor. I'm going to put 10 boxcars on the bottom so that my unit cancels out. When it's on the top and divided by the bottom, they cancel each other out. It's basically saying it's 1. And then 3,000 is what goes on top. So I want you to get that 3,000 crates. And may I emphasize, please use your units. The units are totally key. If you get lazy and just write numbers and don't write your units, you're never going to know what goes on the top and the bottom. So although it's torture sometimes to write out everything, it really helps to keep the conversion factors right side up and upside down to know which way they're supposed to go. Okay, so just a quick statement on what this is. 3,000 crates in 10 boxcars, they're equivalent. So you're basically saying 4 over 4 or 50 over 50. You're saying 1. When you have the same number on top as on the bottom and you divide them, you're saying it's equal to 1. So I can multiply one boxcar by 1 by 1 by 1, and I get the same number of eggs. They're equivalent. Okay, so let me erase those. Okay. So now the unit that I'm in is crates. So now I want to go to my next conversion factor that has crates in it. And what unit am I going to put on the bottom? crates so that I can get rid of crates. So that conversion factor said 5 crates for every 50 dozen eggs we have. Okay, so now my units, crates, has just canceled off. Now I'm almost there. Now I need to get rid of dozens, and I need to get it into the unit that I'm trying to end with, which is eggs. And we know that 12 eggs is in 1 dozen. So where am I going to put? I'm going to put 12 eggs on the bottom or on the top? Well, I'm going to put 1 dozen on the bottom so that my units cancel out. And I'm going to put 12 eggs on the top, so that the only unit I haven't canceled out is eggs, and that's the unit that I'm going to be ending with. Now I need to multiply everything across the top and divide it by everything on the bottom. And I'm going to just plug in here really quickly. Please, please, please use parentheses on the bottom. It's an order of operations issue. And when students don't put those in parentheses, they get the wrong answer. And you'll find out that the hard way, unless you can just remember to do that. So we're going to do the math here. I have my calculator handy here. So I know you don't want to multiply by 1, but I'll just do it. So 1 times 3,000, I'm going across the top, times 50 times 12. And now I'm going to divide it by, in parentheses, everything that's along the bottom. Let me circle those, everything that's on the bottom. Then I'm going to divide it by 10 times, I hope I did this right, 5 times 1. And I'm going to close my parentheses. I'm not going to forget. And I'm going to get the answer 36,000. I hope I did that all right, everybody. No laughing at me if I screwed up while I was talking. So 36,000 eggs are the number of eggs that are in 1 train boxcar. It's also a good idea to look and see if that makes sense, if your answer is a sensible answer. If I said there were 4 billion eggs in that 1 boxcar, I might question the work that I did and might think, okay, I need to look back over that. But 36,000, that seems like a sensible number. If 3,000 crates hold 50 and the 5 crates holds 50 dozen, I feel like that's a sensible answer. All right, so I've shown you how to do conversions. Now let's bring that all back. Let's bring that all back to using moles and molar masses and molecules and all that. So let's take a look at your mole roadmap. One more time, let's say that you start with moles. So let's say I give you 2 moles and I want to know the mass. We're going to start in the middle section and we're going to head down to where it says mass. So the conversion factor for going down, look at the arrow that's pointing down, is the atomic mass over 1 mole. So you're going to multiply the number of moles times the atomic mass over 1 mole. The units will cancel, which you'll see in a moment, and you'll get the mass for 1 or 2 moles of whatever it is I said that I was talking about. I could go the opposite direction. I could start with, let's say you have 25 grams of something, and you want to know how many moles it is. You'll follow the up arrow, and that's where you're going to have 1 mole on the top and atomic mass on the bottom. Remind you what the atomic mass is. That's the mass from the periodic table. So that's where you're looking, and carbon was 12.011 and oxygen is 15.99 or rounded to 16.00. If we want to find out the number of atoms or molecules or particles, then we're going to go to the upper right-hand corner. Right now, we're going to ignore volume. We won't be talking about that at all in this unit. So let's say I tell you you have 5 moles and we want to know how many molecules that is. You're going to go from moles to the arrow that's pointing up toward atoms, and you're going to see that you need 6.02 times 10 to the 23rd atoms on the top over 1 mole. Okay, that's how you use the mole roadmap. I think maybe it's a helpful crutch at first, but please step away from that so that you can do these independently. Okay, so let's see if I can get my image out of our way a little bit here. Let's take a look. So let's do the first conversion. It says, how many moles of carbon are in 26 grams of carbon? So what we're given is what we write down first. So what we were given is 26 grams of carbon. So we write that down first. We want to get rid of grams and convert that into moles. And I see that that's a 1-step process. If I want to go from grams to moles, it's 1 one conversion factor. So according to this, I would put 1 mole on top and the atomic mass on the bottom. But I want you to see that you didn't need to use the mole roadmap to figure that out. I see that I have grams of carbon on top, therefore I want to put grams of carbon on the bottom. I'm trying to figure out how many moles, so the unit that I need is moles. Now, what's super important is any time that you're converting with moles, it's always going to be 1 mole. So when it's part of a conversion factor, look on here, 1 mole, 1 mole, 1 mole, and 1 mole. It's never going to be any other number of moles. That's what the conversion factor is always going to be, 1 mole. Okay, so we've canceled out our grams. We're left with the unit moles. I multiply across the top. Very simple, 26 times 1, nothing to it, divided by 12.01, and I get 2.2 moles of carbon. Maybe type it into your calculator just to make sure that you're seeing how the math on this works. Okay, I'm going to move on to another one. Very similar. How many grams are in 2.5 moles of sugar, sucrose in this case? I think it's sucrose. So anyway, so we're going to take a look. We start this time down in the grams area. So we're down here. We're going to go up to the mole. It's a one-step problem to get to moles. And I see that 1 mole is going to go on the top and the atomic mass is going to go on the bottom. Did I need the mole roadmap to figure that out? Not at all. I write down what I was given, 2.50 moles. Now I know that moles has to go on the bottom. Oh, I was going the wrong direction. How many? I was going the wrong direction, you guys. I said it all backwards. I'm sorry. Let's start that again. You are given moles. The question is, how many grams is it? So here's your moles, and you're going down to grams. My apologies, everybody. So you're going to have mass on top and 1 mole on the bottom. See that the mole roadmap didn't help me at all. It wasn't until I wrote it that I knew I'd screwed that up. Moles is on top here, so moles have to go on the bottom. So you're going to have the conversion factor. Where did I get the number 342.34? That's the mass. 12 carbons plus 22 hydrogens plus 11 oxygens. That's the mass of all of those atoms added together. That's the atomic mass. So I got that from the periodic table. And then it's all in 1 mole. So I multiply across the top this time, 2.5 times 3.4 or 342.34 grams. And my answer is in grams, 855.8 grams. Pause, double check your math, make sure that you're understanding how to do this. Okay, I'm going to move on. Let's try one more. Now we're going to go into the upper right-hand corner this time. It says how many molecules, that's what we're trying to get to, if we're given 2.5 moles of the same substance from last time. So again, we're starting in the center circle and we're going to head up this direction. So when we're trying to calculate the number of moles, the number of atoms or molecules in 1 mole, that's where we have to use Avogadro's number. So let's write down what they gave us. They gave us 2.5 moles. I know that in my conversion factor, the unit has to be moles on the bottom for it to cancel out. And when I'm doing conversion factors, it's always going to be 1 mole. On the top is going to be Avogadro's number, so 6.02 times 10 to the 23rd molecules. Now I multiply that out, 2.5 times 6.02 times 10 to the 23rd divided by 1, who cares, equals, and that gives us our answer. Double check your math. Would you also make sure, take a look at your calculator? A lot of you are going to see a number that confuses you when you get into these big numbers. It will say E23 or E24. That means exponent. So what that is, it's a shorthand way of your calculator writing 10 times or 10 to the 23rd power or 10 to the 24th power. So if it says E23 or E24, that means times 10 to the 23rd or times 10 to the 24th. Don't write it E23 or E24. That shows me that you don't know what that means. So when you write it, your answer should be 1.51 times 10 to the 24, even if your calculator said 1.51 E24. That's not how you write it. You write it times 10 to the 24th. All right, let's do one last one, and this one is a harder one. So it says find the mass of 2.1 times 10 to the 24th molecules. So we're starting in the upper right-hand corner of the mole roadmap. And we want to find mass, so we need to go all the way down to the bottom of the mole roadmap. That's 2 steps. Remember when we did the eggs in the boxcar, we had 3 steps? This is a 2-step conversion problem. So the first thing that we're going to do is write down what they gave us. So they gave us molecules. So we're going to write down molecules. That means that the unit in the first conversion factor that's on the bottom has to be molecules. The only one that includes molecules is the one that has Avogadro's number in it. So that's 1 mole over 6.02 times 10 to the 23rd molecules. Do you see that molecules here and molecules here canceled out? Now, technically, I'm in the unit of moles. So for my next conversion factor, when I go to the next step, what unit do I have to put on the bottom? Moles to make it cancel out. So 1 mole on the bottom, and I'm trying to get it into grams. And so notice that that unit never gets canceled. So I've crossed out, I've divided out all my units, and I'm left with 84.01 grams. I multiply everything across the top. Be careful. Please do this in your calculator right now to make sure you get the same answer. You need to do 2.1 times 10 to the 24th times 1 times 84.01 divided by parentheses 6.02 times 10 to the 23rd times 1, close parentheses. Make sure that you close that parentheses. Try it without closing the parentheses and see what happens. And so make sure you get the right answer. Now, here it says the answer is 290 grams of NaHCO3. That is rounded for significant figures. So what your calculator is going to tell you is 293.058, blah, blah, blah. You're not going to report all those numbers. I told you that you should report 2 decimals. That's not following sig figs, but if you tell me 2 decimals, I'll be happy. So you should get 293.06 for an answer. So let me know if you have any questions about that. All right, everybody, that is it. Tonight you have homework called Intro to Mole Conversions. It's found on Canvas and it's due tomorrow. There is a video answer key, so you can see me working through the problem. Skip ahead to, if you're fine with problem 1 and 2, but you need help with 3, skip ahead in the video so you can watch how to do problem number 3. Unfortunately, when I recorded the video, I made 2 mistakes that I didn't notice. How is that possible? I have no idea. So I wrote the corrections on Canvas so that you can see the mistakes. So be sure that you aren't misled by my screwing up on the video and that you pay attention to which ones I messed up. Okay, everybody, hope you have a great day. Let me know if you have any questions.